What we're going to do is to give you everybody a chance, everybody who has, even people who have not heard about logit and probit regression, a chance to understand what it's all about in a couple of slides, and then quickly add the multi-level complication to it. And we're going to show an example of how to do multi-level regression in Mplus. So if you look at the right screen, slide 39, you have a model in equation 22. And some things are similar to before and some things are new. What's similar is that you have a linear regression piece sitting in these brackets. It's an intercept beta 0, a slope beta 1 for a covariate x1, and a slope beta 2 for another covariate x2. And we're going to be interested in seeing how those x1 and x2 variables influence an outcome. But the outcome is now dichotomous. It's a variable u. In Mplus nomenclature, that's a categorical variable. In this case, it's a dichotomous variable, binary variable, that assumes values 1 and 0. And in linear regression, we talk about x is predicting a value of y. But here we're going to talk about x is predicting a probability for u, a probability instead of a value. Nevertheless, it's the same kind of idea. We predict the dependent variables, individual outcomes, in this case, probabilities. So we have then an equation which looks linear inside of the brackets, but this f function of this linear expression is a nonlinear function, which makes the probability expression a nonlinear function of the axis. And the f function, with a general argument of z, it's either a standard normal distribution function, written as cap phi, Greek letter, or a much simpler logistic function, 1 divided by 1 plus e to the power of minus z, which is the logistic function that you use in logistic regression. In both of these cases, do you have a, I'll put these slides up like this. In both the normal distribution function phi case and in the logistic, do you have a, is this equation 22 representing a nonlinear regression? A nonlinear regression, which you need because you have a probability varying between 0 and 1, and you can't allow these values to be predicted outside of the range greater than 1 or less than 0. So you want to have this S-shaped curve, and the betas, the intercept and slopes, are affecting the shape of the curve. This is true for both logit and probit regression. Probit regression is the model we have when we work with the f being the phi function, the standard normal distribution function. And logistic regression is what we get when we use a logistic distribution function. But both of them have that kind of S-shaped form. So just to make it a little bit more tangible, look at the example on your slide 39 at the bottom. Say that U is an individual having lung cancer or not. U equals 1 is lung cancer. And this is then coal miners and smoking related. So X1 is a dichotomous covariate, smoker, non-smoker, and X2 is a continuous covariate year spent in coal mine. So we can then represent that pictorially as the probability of lung cancer as a function of the continuous variable X2, years spent in coal mine, where the dichotomous variable is captured by the curves, by two different curves lying side by side like this. So that for a given number of years in a coal mine, for a given value of X2, if you have X1 equals 0, you have a lower probability of getting lung cancer than if X1 was 1. So you can imagine then that X1 equals 1 implies that you're a smoker. And that's what a slope beta 1 does for a categorical variable, for a dichotomous predictor. It just shifts the curve sideways, whereas the steepness of the curve is governed by the slope for X2, namely beta 2. So in this case, beta 2 is positive. So you may want to scribble beta sub 2 greater than 0 here. So it is positive, a positive influence. If beta 2 was negative, the curve would come down like this in the mirror image. What's inside of this bracket is the so-called logit or probit, and that is linear in X. So you would have these lines instead that are parallel, much like ANCOVA with a covariate X2, X1 being the treatment control variable, so to speak. Now, when it comes to working with logit and probit coefficients, and we'll focus on logit here, there are the different levels of ambition that you can have in interpreting the results from an analysis, estimating these coefficients, particularly beta 1 and beta 2. You can just focus on the sign, be it positive or negative, is it positive or negative, and its significance. Or you can try to express the results in terms of odds and odds ratios, which is very popular in terms of logit analysis. Or, more down to earth perhaps, just focus on the probabilities that the model implies, which is after all where the model starts. It is a model for probabilities. All of this carries over to two-level modeling, and also we encountered this type of outcome modeling in the growth situation yesterday for the binary part of the two-part model. And since we talked about the two-part model, word spread across the country, and we actually have the author of that two-part article I mentioned. He came specifically to the course here, so Rick Brown is sitting here in the front row now. And you can ask him about his intervention study. He remembers which parts were significant, which weren't. So here is a heavy-looking page, but we love the formulas, don't we? So just briefly, we're going to talk about odds. Odds for u being 1 is really, an odds is really a ratio of probabilities. Probability that you get lung cancer divided by probability that you don't get lung cancer, where probability u equals 0 is simply 1 minus probability u equals 1. We agreed that the logistic function was this one, this familiar expression from logistic regression. That's what gave the S-shaped nonlinear curve. Why is this so loved, this function? More loved than the probit function? Well, it's because it gives a simple interpretation for odds via log of odds. The log of odds are linear in X. So the log of odds is what we call a logit. So here we define a logit. Logit is the log of the odds, where the odds is the ratio of the probabilities. Why is this vibrating? The whole room is shaking. So logit is the log of an odds, that is a log of a probability ratio. And if you insert this formula for the probabilities into this and go through the algebra here, very simple high school algebra, out comes the linear expression. So the logit is this simple linear expression. And therefore, the log odds is linear in x. And taking it further then, if you don't like log odds but prefer odds, well then you exponentiate the left-hand side and the right-hand side, and you end up exponentiating beta 1 to get the effect of x in terms of odds. So that's summarized on page 43 here, slide 43 rather. The logit is a log odds, which is linear in x. And the interpretation is that when x changes 1 unit, the logit, the log odd, changes beta 1 units. Just like regular linear regression, but the y variable, so to speak, y variable is now a logit. So when x changes 1 unit, the logit changes beta 1 units. Or when x changes 1 unit, the odds changes, odds instead of log odds, changes e to the power, the exponentiated beta slope units. Okay, that was a 10-week course on logistic regression in 5 minutes. How do you feel about that? So now we're going to do 2-level logistic regression. And take our time then to think about slide 44. So again, following the notation of Linda's discussion this morning, earlier, we have J denoting cluster, I denoting individual, and the logit for individual I in cluster J is the log odds, the log of the probability ratio, which is this linear function of x. But now the novelty is that the intercept and the slope have subscripts j, allowing for variation in the intercept and the slope across the cluster units. So this would then be, if you want to, this is equation 1, and this is the level 2 equations 2a and 2b, where we represent the variation in the intercept and slope, where alpha and beta are the means, and the U0, U1 are the residuals, so that the residual variances here are the same as the variances of alpha and beta. So the mean of alpha and beta are alpha j, beta j are alpha and beta, and the variances of alpha j and beta j are the variance of U0 and U1. Just perfectly analogous with what we talked about before. So imagine that you predict a dichotomous dependent variable, u equals 1. Then you would use, but you have that in a cluster sample setting. Then you have this single predictor here. This is your level 1 predictor. In this case, I have no level 2 predictors, no w sub j's in Linda's notation. But I have this within level 1 predictor, and I have these alpha and beta values. Let's say that, let's focus on the intercept for a second. After all, in most situations, it's the intercept that has a significant variation, much, much less often the slope. In fact, in many analysis that you see in particles, people don't even talk about random slopes. They say they do 2-level analysis. What they've done is take into account random intercepts, and that's most often sufficient. So, like, I just want to emphasize what Linda said. Don't make every single slope in your complicated models random. You'll just suffer from it. Start with random intercepts, certainly. But what does this mean then? Linda talked about cross-level influences. That is, we often have an interest in seeing what the cluster effect is on the individual. So for instance, a classroom environment, how does it influence a student's behavior? And what we're looking at here is a very dramatic story expressed in these formulas. We're saying that the logit, the odds of you behaving in a certain way, u equals 0, say that that's bad behavior, and u equals 1, rather, bad behavior, u equals 0 is good behavior, probability, or the odds that you're going to behave badly, is a function of your individual characteristics, your background that you bring with you to this classroom. But it's also a function of alpha j here. That is, if you have no subscript j here for a second, it's also a function of alpha j, which is a classroom characteristic. It's not measured. It's an unobserved heterogeneity. It's a latent continuous variable, alpha j. It's a latent continuous variable, but it is a classroom characteristic. Certainly you can try to measure it or measure predictors of its variation, but let's ignore that for the moment. It's a classroom characteristic, alpha j. There's a particularly high alpha j value. Say a classroom particularly high alpha j value would mean a high logit, a high log odds. That is a high probability of behaving badly. So we're going to take a look at examples like aggressive disruptive behavior in the classroom. So the probability that a student behaves aggressively, disruptively, is a function of the student's characteristics, background variables, but it's also a function of the classroom characteristics. So a high alpha j value would mean that the classroom produces a high probability of behaving badly. So if you take two students with the same x values, they may have different probability of behaving badly because their alpha j values are different. One alpha j from one classroom and another alpha from another classroom. So therefore, you're very interested in the variation in alpha j. Is there a big variation across classroom? Because if so, then the classroom environment has a big effect on your probability of your behavior. That's how you should think about this. You should make these formulas come alive to the extent that you have the energy to do so. So, we have an example. And Nick Alonga is in the room. So this is predicting juvenile delinquency from first grade aggressive behavior. And this is cohort 1 data. And we're looking at over 1,000 students in about 40 classrooms. And we're going to focus on fall of first grade in terms of the aggressive behavior. But we're going to predict to juvenile delinquency recorded, I think, by age 18 or something like that. Juvenile delinquency then being our dichotomous U variable. And we're going to perhaps bring in covariates like gender and teacher-rated aggressive behavior to try to predict. So let me do it this way. Here's the Mplus setup for this. This all took place at Johns Hopkins, Baltimore Public Schools. Here's the data set I was given, borrowed for a while. Here's the names list. And we see that we have a bunch of fall of first grade aggressive behavior items. We recognize our familiar stubborn item from yesterday afternoon. Cluster here is classroom. And we're going to use the variables juv99, this is the dichotomous dependent variable, the U variable. That's juvenile delinquency. And we have a covariate male. Male equals 1, a female equals 0. We do a little fancy redefinition of the gender variable so that variable male is 1 when the person is male, and it's 0 when the person is female. And then we have aggress. Aggress is then simply a sum of these, 9 aggression items, which are Likert scale items, basically. So it's a sum in this case. And we declared the dependent variable as categorical. Mplus then finds out that it actually has 2 values, but it could have multiple values. We could work with an ordered categorical logistic regression. We define missing data symbol. And in line with what Linda said, male and aggressiveness are variables measured on the individual level and modeled only on the, measured on the for the students and modeled only on the within level. That was so nicely stated, I think we have to create a slide with that text. So here's the analysis. We do two-level analysis, and we take missing data into account. And here's a little feature, process equal 2. This is sort of an encouragement for you to get computers with multiple processes, because the more processes you have, the faster it goes. And for those of you who don't know what multiple processes are, a single process machine is when there's only one person sitting inside of the computer doing computing. And here it's 2. And I am enjoying a 4-processor machine right now, which makes it go a lot faster. And apparently one can have, in version 5, 8 or more processes activated. And the model is having a within and a between part. On the within part, we say juvenile delinquency on male and aggressiveness. And on the between part, we say nothing. Nothing. We don't have to. The rest is default. And what is the rest? Well, on the within list, we put male and aggressiveness behavior, but we did not put the third use variable, juv99, which then, by Linda's rule, means that juv99 is allowed to be modeled on both levels. Juv99 is not on the within list, nor is it on a between list. So it is a student level variable that is allowed to be modeled on both levels, which implies that Mplus takes the default approach of letting its intercept be random. The intercept is random. So you could, if you really insisted, you could say juv99 semicolon here. Same thing. That is, the variance of this is estimated on the between level. So if you say juv99 here, it's the same thing as saying nothing in this case. So just try to remember now, the outcome on level 1 is dichotomous. And logistic regression has no variance parameter in it. It just has the beta 0 and the beta slopes, right? There's no residual variance like we have in linear regression. There is no such free parameter to be estimated. So but then on level 2, this is a random. This becomes a random slope. Juv99 is a random intercept, which is a continuous latent variable that has a variance. So on level 2, juv99 is a continuous latent variable which has a variance and could very well be regressed on classroom characteristics. I just didn't do that here. So no level 1 variance for a dichotomous variable, but a level 2 variance. So the results are, I'll put it on this slide too if you prefer. On the within level, you get juv99 on male and aggression. They are the fixed slopes. The fixed slopes come out on the within level. There's no across classroom variation in those, as we have specified. One could try to tease it out, but we didn't. And juvenile delinquency has a positive significant coefficient here, which means that if you are a male as opposed to a female, you are more likely to have a juvenile delinquency event by age 18. More likely. Significantly more likely to have it if you're a male rather than a female. And as your aggressive behavior in fall of first grade increases, you are significantly more likely to have a juvenile delinquency by age 18. That's a pretty nifty finding, right? That you can predict from fall of first grade. So a teacher looking at your kids can predict what's going to happen to them. That's scary. I don't know how well they will predict. You know, there's going to be a lot of false positives probably, but it is significant certainly. You can try to figure out how big this effect is by looking at log odds, odds, and probability statements that you can generate from this model. Now on the between level, we get a threshold that we're not even going to bother talking about right now, but let's look at the variance. What is variance Juve 99 here? Well, on the between level, Juve 99 we agreed was a random intercept and therefore a continuous latent variable, random intercept, and it has a positive variance. It should be positive, otherwise we're not doing modeling very well. And it has a small standard error relative to its point estimate, so that the so-called z-score is significant on the 5% level. So it looks like we have a healthy across-classroom variation in juvenile delinquency. That is, classroom effects are important for first-grade classroom environment in terms of aggressive disruptive behavior is predictive of juvenile delinquency. If you have two kids with the same background variables, same gender and aggressive behavior development, the kid who is in a more highly aggressive classroom would be more likely to experience juvenile delinquency later on. That's what this says. So this is standard two-level logistic regression. Mplus does that by full maximum likelihood. There are quasi approaches in software. PQL, I think, is one such thing which has bias for certain situations. But this is the full ML approach. It's fairly fast computation, at least if you do only a random intercept. If you bring in random slopes, you're going to incur more and more dimensions of so-called numerical integration. And you're going to be more and more dependent on having many processors for that to go quickly. But with the random intercept, it goes very quickly, no problem. Now, how do you understand the between-level intercept variance in this case? Well, we started out talking about intra-class correlations, and there is a way to compute ICCs here as well. Basically, what you do is take the between-level variance, 0.807, put it in the numerator, and in the denominator, you use as the within-level variance pi square over 3. Of course, right? So that is, thank you, Nick. Take your time. Pi square over 3 is, as we all know, the variance of the logistic density. It's not a parameter that you estimate, but you do have a variance there implicitly. Within variance, and it's pi square over 3. And some people then argue that therefore you can compute an ICC based on this same formula, between divided by within plus between. Now, other people, like my former postdoc, Klaus Larsen, wrote an interesting paper in American Journal of Epi based on a biometrics article where he talks about how to interpret between-level intercept variance in terms of odds ratios. And he does that in the context of neighborhood effects on individual health. That's a good read, I think, for applied folks. He proposes more, probably because the acronym is chosen, probably because it means mother in Scandinavian languages. And you know how that is. Consider, they have influence beyond. I'll stop there. Consider two persons with the same covariates chosen randomly from two different clusters, two different classrooms in this case. The more is the median odds ratio between the person of higher propensity to behave badly and the person of lower propensity. Ponder that statement. But it's trying to interpret the classroom effect, the variation in alpha j. And more is then clearly expressed this way. And you may want to draw the square root sign over here. Square root sign goes over here. And phi is then the standard normal distribution function inverted. Inverted means that starting from the p-value, you go to the z-score. So if you look through the article, you will see this explicated in detail. In the current example, the ICC is 0.20, so we would say that that's a fairly healthy ICC. Although Larson argues that ICCs aren't as meaningful because we don't have an individual level variance that is a free parameter. He instead focuses on the more, which is an odds ratio, and odds ratios greater than 2 are noticeable odds ratios. For those of you who do epi studies of logistic regression, I think you agree that an odds ratio of 2 or larger is an important one. So it would be 2.36 in this case. I don't know if he's calculated standard errors for mores, so we can get confidence intervals. Anyway, this is not something that Mplus gives you, but you can compute it easily by hand. I succeeded, actually, very easily through these simple formulas. Now, you can always bring it down to something very tangible. And most tangible thing, I think, are the probabilities. And, the model talks about probabilities. And if you go back to the original formula that I showed you, slide 44, this formula gives you the logit, and from the logit you can compute the probability. And what you could do, simply in terms of probability, you can look at the random intercept, and there's a variation in the random intercept, and you can consider a value of the random intercept 1 standard deviation above and 1 standard deviation below the mean of the random intercept. For instance, so classrooms that are especially aggressive disruptive on average, and classrooms that have a lower level of aggressive behavior, you can actually insert those values into this formula together with the estimated beta slope, say, the beta slope, and the person's x value, and compute the logit, which will give you the probability by the previous pages. And then just see what's the difference in the probabilities, because the probabilities really have a tangible interpretation. I'm focusing on this a little bit more than I otherwise would, because we're going to use this when we get into categorical latent variables tomorrow, where we have a latent class variable, a latent variable that is categorical, say dichotomous, and we're going to have a regression of that latent class variable onto covariates, and we're going to do that in a multi-level fashion. So we're going to have random intercepts for latent class variables. But that's the same idea as the random intercept for a logistic regression here, that alpha j idea comes in. There's a variation in the intercept, which then reflects the impact of the cluster level environment on the individual. And then I think it's time for Linda. Taking that idea one step further.
Okay. So now we're going down our list of multi-level models that we're looking at, and we're coming to a path model. So it's going to be a multi-level path model with a binary outcome and a mediator with missing data. So if you take a look at this first slide and the logistic regression, this is just not a multi-level, but just a single-level logistic regression. And this is how this type of data might be analyzed traditionally, where you have a dichotomous variable, high school dropout, and a set of covariates here on the left, female, mother's education, etc., math 7 and math 10, and you would just do a logistic regression with high school dropout regressed on that set of covariates. Now you can make an extension of that model where you take into effect, or where you consider the fact that math 7 is measured before math 10. So including them both as covariates in a single level model might not actually be making the best use of that variable. It might be better to pull Math 10 out, as we do in the path model on the right, and then have it be a mediator, and perhaps an early warning signal of potential to drop out of high school. Another reason that it's good to bring it in as a mediator is something that came up earlier today, and that's the fact that Math 10 has a lot of missing data. And if we leave it as a covariate, then every case that has a missing value on Math 10 will be eliminated from the analysis because there is no missing data theory for covariates. But if you pull it out and bring it in as a mediator, then it's now a dependent variable in the model, not an independent variable. So then, and we can also look at the direct effect of high school dropout on these covariates and also the indirect effect going from the covariates to Math 10 to high school dropout. So just by making that one change in the single level model, we come up with a more interesting model to look at. But we can take that a step further, and we can consider a two-level path analysis. So what we've done is we've taken the model, the path model, and we put it on the within level. And then the filled circles represent the fact that we're going to have random intercepts in both the regression of Math 10 on the covariates and high school dropout on the covariates and Math 10. We won't have random slopes. If we did, we'd have filled circles on these arrows. So the within model will be random intercepts only. And on the between level, we have these random intercepts as continuous latent variables. So this is the intercept for Math 10. It's a variable. It has variation. It's a random effect. It's going to have a mean and a variance. And the same thing for high school dropout. Now, we could extend the between model to have a set of between-level covariates that we regress Math 10 and high school dropout on. So we could have a box here with some between-level covariates, but we'll keep it simple for now. So let's take a look at the input that we would need to use in Mplus to estimate this model. Everything's pretty much the same as we've been looking at, except now we have to use the categorical option to identify high school dropout as a categorical variable so that the proper estimation will be used. So we have several options like categorical, nominal, count. These options are only for dependent variables in the model, not for independent variables. Independent variables can be either binary or continuous, and in both cases they're treated as continuous variables as in regular regression. We have our cluster and we have within, so you'll note that we're putting all of the variables here that we're using on the within list. That means that they'll be modeled only on the within level. If we didn't, they would be modeled on both levels. And we have two-level missing, which we're familiar with. Estimator equals ML. I think the default is MLR, so we're asking to use ML. And then two important things. Because we're doing a multi-level model and because high school dropout is categorical, then numerical integration is required. So we specify algorithm equals integration. And because Math 10 has missing data, the only type of integration we can use is Monte Carlo integration. So we specify integration equals Monte Carlo, and in parentheses, a total of 500 integration points. So this is what will make the analysis slower. I think each of the random intercepts is one dimension of integration. And if you have more than 4 dimensions of integration, it really becomes an untenable model, no matter how many processors you have. And isn't estimated with enough stability to be meaningful then. So on the model command, we can relate this to the path diagram. we use on the within level, so percent within percent, we regress high school dropout on this whole set of covariates, female, everything here. And then we regress math 10 on the covariates. So high school dropout is regressed on math 10 and the covariates, and math 10 just on the set of covariates in the box. And on the between level, we have the variance for high school dropout and math 10. And we're showing that we're giving them starting values of 1. We must have needed that to help with convergence. Do you remember why? Okay, we don't remember why. And in the output command, we ask for a variety of options that aren't really probably that important for this discussion. So the important things is that the intercepts are random, that we have a mediator, and that because of that, missing data on that, we have to use Monte Carlo integration. And on the between level, we have the 2 random intercepts. The random intercept for high school dropout and for math 10. Now we have our normal summary of data where we just show the number of clusters, 44, so that falls within the number that we say is the minimum, 30 to 50. And then let's just go to the model results on slide 57. So here, first of all, let's remind ourselves of one thing in the picture. So high school dropout is a categorical variable. It's binary. So that means that the high school dropout regression is a logistic regression using maximum likelihood estimation in Mplus. Now you can also have probit regression with maximum likelihood, but the default is logistic, which we're using. So that's a dichotomous variable. The scale of the dependent variable defines the kind of regression. So math 10 is a continuous variable. So we're going to be having a linear regression for that. So when we interpret our results, we have to remember that the estimates for the regression of high school dropout on the covariates are logistic regression coefficients. Whereas on the next slide, the regression coefficients for math 10 on the covariates are linear regression coefficients. So let's just go back now to our the logistic regression coefficients. As Banks said, it's usually sufficient to look at sign and significance, but you can turn logistic regression coefficients into odds ratios, and I think we do that automatically in most cases in Mplus now. And you can also compute probabilities for them, which may be an easier way to interpret them. But what do we have here? So female is not significant. So mother's education is significant, but it's negative. So you would say as mother's education increases, the likelihood of dropping out decreases. So when we're talking about logistic regression coefficients or probit, we're talking about likelihoods. So here's another covariate that's significant, expect, which is expectations of further education. So as that increases, the likelihood, once again, of dropping out of high school decreases. Let's look down here at dropout thoughts. So as dropout thoughts increase, the likelihood of dropping out increases. So that's how you would take a look at the results here and how you would interpret that. Now with Math 10, these are linear regression coefficients. So let's take a look at let's see, home resources. So as home resources increase, Math 10 scores increase because this is a positive, significant relationship. So now we're back not to talking about likelihoods, but talking about values because this is a simple linear regression coefficient. Now let's see, Math 10 let's look over here. High school dropout on Math 10. Actually, we should go back and look at that and see what that looks like. So high school dropout on Math 10 is significant negatively. So as Math 10 increases, high school dropout decreases. So it's important how people are doing on math in the 10th grade as far as the relationship to dropping out later. So that's another coefficient that you might want to look at. And you could compute in Mplus the direct and indirect effects here between the various covariates and high school dropout in Math 10. So what do we have here? We have residual variance of Math 10. What does that say? It's highly significant, so that's telling us that in this regression, there's a lot more variability to be explained, even though we have a large set of covariates. And variances of high school dropout in Math 10 on the between level, those are the variances of the intercept, the random intercepts. And once again, they're significant, which could imply that maybe we could have covariates on the between level to explain that variability. So I think it's sometimes hard to get one's mind around the fact that high school dropout is a dichotomous variable on the observed level. And how can we be calling it continuous on the between level? Well, because it's the random intercept in the regression of the dichotomous variable high school dropout on a set of covariates. So it's a random intercept, and it is a continuous variable. It actually took us a long time to get our own minds around this 8 years ago or whenever we started doing this. So this is why we come up with drawing the diagrams with circles on the between level to remind ourselves that they're continuous variables on the within level. So what does that mean? If you decided to add covariates, then these are continuous variables, so both of those regressions would be linear regressions because the scale of the dependent variable defines the type of regression. And I think it's your turn again. Oh, yes.
Okay, so this is then a mediational example, and there's been a lot of interest in mediation in multi-level models recently in journals like PsychMethods. And here's one example. Bauer, Preacher, and Jill have written an article on that, where they, and others before them actually, talking about this situation where you have X and Y and a mediator M, and the slopes being denoted A, B, and C prime. Many of you have probably seen that mediational picture in the single level setting, but now the coefficients have subscript J for clusters. And the indirect effect is usually, in the single level context, it's A times B. Actually, then I noticed that you should change that plus sign to a multiplication sign. The plus sign should be a multiplication sign between alpha and beta on slide 60. And in single level modeling, that is the indirect effect, the product of the two slopes. Whereas in multi-level modeling, you have to add that covariance term between alpha and beta. The indirect effect is a little bit more complex. So Bauer et al. Talk about that in the Psychological Methods article. We just wanted to show that Mplus has been able to do this for a while, and we want to advertise that it can do it by giving you the input for a two-level mediation model with these random slopes. And we do so actually in a Monte Carlo setting. So I'll just briefly describe how you do Monte Carlo simulations here in the this really simple setting of two-level mediation with random slopes. So you say you have variables y, m, and x is a within variable. We don't model it on between. And we have a model population here where on the within level we define random slope for y on x, that's C, y on m, that's B, and M on X, that's A. We give some hypothesized variances for these, and on the between level, we give hypothesized covariances between the intercept, which is Y. Y is the intercept on the between level, the intercept in the regression of Y on M and X. And its covariance with the other random effects. And M, its covariances with the random effects. And A, its covariances with the other random effects. So we get a hypothesized model there with hypothesized parameter values. And we want to generate data according to that model and analyze it as a two-level random model. Here is the model. The model is exactly the same as the population generating, as a data generating model. So if you go back one step here, I should have this on this slide. Model population says what the model is in the population from which you draw random samples. The model statement on your right here is how you analyze the data. And here we analyze the data exactly the way it was generated. And you may say, well, what's the point? Well, I don't know. But I think it's, you want to see that you can recover these parameter estimates well and get good standard errors for them. And you don't know what kind of sample sizes you need to do so. Here we have postulated that we work with a sample size of 1,000, and we have 100 clusters of size 10. 100 clusters of size 10. And we want to know if 100 clusters of size 10 is sufficient to estimate these parameters well. And if so, if that is found sufficient, can we get away with 50 clusters? Can we get away with 25 clusters? And here, down in model constraint then, if you look at slide 62, model constraint, you can actually define your own random effect here. Or sorry, your own indirect effect. Going by this formula, the indirect effect is the coefficients alpha and beta multiplied, MA times MB, those are the slopes here, and plus CAB, which is covariance. So you pick up those parameters, MA and MB, they are labels put next to a certain coefficient. They're labels, and those labels are then repeated in the model constraint setting. Then the output is as follows. Two-level mediation. You have the within level, and you have the between level. And on the next slide, 64, which we'll focus on, you have the new additional parameters. Here, M here at the bottom of slide 64 is the indirect effect. The indirect effect. And the way you look at this is that the first column is the population values. The population indirect effect is 0.3. The second column, you have the column headings on the previous page. The second column is the average estimate, because we draw, I think, 100 samples from this population. If you go back and take a look at it, we draw number of replications. NREP here means that we draw 100 different samples of size 1,000. So NREP is 100 samples that we draw. So across those 100 samples, the average estimate of the indirect effect is 0.29, which is very close to 0.3. So we do very well here in recovering the population value. Likewise, the average standard error, these two columns refer to the average standard error and the variation, empirical variation across these replications in the parameter estimates. So these two columns should agree well also, and they do very well. And coming then to the second to the last column, if you go back to slide 63, it is the 95% coverage. That is the confidence interval. You want to have confidence intervals around parameter estimates. that cover the true parameter value 95% of the time when you use the 95% confidence intervals. So the true value is going to be 0.95 down here. Should be 0.95. And it comes out to be exactly 0.95. And in the last column, which on the previous page is labeled percent significant coefficient, the last column is 0.55. This is the power. This is an estimate of the power at the bottom of slide 64. It says in 55% of the replications that we're doing, we can reject the hypothesis that there is no indirect effect, no mediated effect. But we really want the power of at least 0.80. So this is a low power. This is a low power in this setting. We have too low of a power to detect an indirect effect when the slopes vary across the clusters. So that tells you two things very quickly. One, that we can do in Mplus two-level mediation even with random slopes. Second thing, we can do a Monte Carlo study of it. I went through the Monte Carlo study very quickly, partly because I don't want that to be a focus right now, but also because it is explained very nicely in that Mutena article from 2002 that we talked about yesterday. If you weren't here yesterday, you can email us and we'll tell you exactly which article that is. But we just want you to know that two-level mediation is alive and well in the Mplus context. So now, Linda, should we take questions at this point, or what are we?
I think you should start two-level factor analysis.
Yeah, so let's take a deep breath and start two-level factor analysis. Excuse me, to get a good head start for this afternoon. So far we've covered in the list of analysis techniques that you may want to take to the multi-level level. We've talked about regression analysis. We talked about path analysis with mediation. Now we want to talk about factor analysis. And we started off today with a random effects ANOVA on top left here. A random effects ANOVA, individual I in cluster J. Y is decomposed into a mean part and a between variation component and a within variation component. We may even call the between component YBJ. So YBJ is actually this part then. And YWJ is simply the same as epsilon, the within variation. That general decomposition into a between component and a within component that are uncorrelated is done in two-level factor analysis. That is, you have then a factor model for between and a factor model for within. So the YBJ is explicated, is decomposed into a factor and its residual on the between level, with between level loadings, lambda b, and the within variation is decomposed into within factor and its residuals with factor loadings, lambda w. If you look at the covariance structure then, the variance of y is the variance between variance and the within variance. Sigma is the covariance matrix notation. Sigma between plus sigma within. And each of those covariance matrices has the standard factor analytic covariance structure, lambda psi lambda prime plus theta, and for B subscripts and for W subscripts. And two ways of looking at this. It could be clarifying to think them through. The first way of looking at this is it's simply a variance decomposition So you start with random effects ANOVA and just decompose the variability of y into between clusters and within clusters and give each part a factor structure. But there's another way of looking at it, and that is that you're really working with a random intercept model here. It's a random intercept model. It hasn't been stressed enough, I think, in the factor analysis literature. It becomes clear that it's a random intercept model when you start talking about the possibility of having random slopes. There are no random slopes here. How do you see that? Well, you see that the lambdas do not have subscript j. We're saying that the factor loadings do not change across the clusters. We only have a variation across clusters in YBJ, and we agreed earlier today, I think you agreed, that that was a random intercept model. It's just that that random intercept is explicated into a factor and a residual part. So to make a long story short, if you don't mind, please think of this two-level factor analysis model as a random intercept model. And as we've agreed, random intercept is what you mostly need to be concerned with. There's less reason to have random slopes. We will talk about random slopes model in the SEM context a little bit later this afternoon. But for now, the random intercept conceptualization is sufficient. Here is a paper that you may want to take a look at if you're interested in this. I sat down with Albert Satora in the early 90s and worked through a paper that came out in the book, the annual book, Sociological Methodology, where we talk about complex survey data structural equation modeling. And we did a little Monte Carlo study using two-level data. We generated data with 200 clusters of varying size and varying interclass correlations across the variables. And we used a latent variable model with 10 variables, 2 factors, and we tried to then analyze by conventional maximum likelihood using the regular sample covariance matrix. And we had a simple setting here. We have both lambda between and lambda within having this simple structure with, where each variable loads on only one factor. The first 1, 2, 3, 4, 5 loading on factor 1, the first column, and the last 5 variables loading on factor 2. And it is using the model on the left here with the restriction, though, that lambda is the same for the two levels. Lambda b is equal to lambda w. And this is the first case, I think, where we can get back to the topic of aggregatability. We said that we had a sampling perspective where we looked at aggregated modeling, and we had the multi-level perspective where we looked at disaggregated modeling. Aggregated modeling worked with the same parameters as in a regular single-level analysis, but the disaggregated model added parameters for each level. We said also that a regression model is a model where it is perfectly fine to simply correct your standard errors and keeping the same parameter estimates. You don't get any parameter estimate bias. In this case, you will only get correct parameter estimates if you have equality of these loading matrices across levels. Then, if that equality holds, that is, you have one single lambda, then you can write the covariance structure this way, which says that you still have that lambda sine lambda prime plus theta construction. It's just that psi is the sum of the within and between, and theta is the sum of between and within. But the structure holds, which means technically that the model is still right. The model is still right. There's no parameter bias, but we do have to consider the standard errors. So this is a model, actually, to put it practically. If you have a factor analysis model, you very often do not have this equality, which means that the model is not aggregatable. It would not be correct to simply say type equals complex. It's not sufficient to just correct the standard errors. You have to also you have to do type equals 2 level modeling to get the right parameter estimates and standard errors. We did a little simulation study here. We generated 2-level data with different cluster sizes and different intra-class correlations. And we focused on chi-square and the misestimation of chi-square. And if you remember, I said that standard errors are underestimated if you ignore the clustering. But chi-square then is the opposite. Chi-square is overestimated if you ignore clustering. So we generate data according to a cluster model, but analyze it by regular single-level analysis. So we do what SEM people have done for decades. We ignore the clustering, and we should therefore expect inflated chi-square values. So if you look down here, for cluster size, say 7, and interclass correlation 0.20, the 5% reject frequency is 23.5. It should be only 5% here. It should only be 5. So we're going to reject the model 4 or 5 times too many. And if you have even bigger cluster sizes, you know, the def goes up, as we remember, and you're going to reject the model all the time, 99% of the time at the 5% level. So even though the model is right, you're going to reject it. So you may have a lot of models in your drawers that were rejected, and you can brush them off now and dust them off, and they may fit if you take the clustering into account. But you have to do 2-level modeling to do that. But it really shows that simple formula for def that was derived from a very special case of equal cluster sizes and the mean estimate seems to hold true also in these more general models. That is, that it's the product of the size of the intra-class correlation and the cluster size that makes the problem bigger. Problem being ignoring the non-independence due to clustering. So again, we did a simulation, generated data according to 2 levels, analyzed by ignoring that, and we make these errors. So to repeat Linda's random effects ANOVA story a little bit this morning, 2-level factor analysis of design effects. So regular analysis, ignoring clustering, gives you inflated chi-square and underestimated standard errors. Type equals complex gives you correct chi-square and standard errors, but only if the model is aggregatable. And in this case, the loading matrices have to be the same on the 2 levels. I would say that's the exception rather than the rule. Many other models aggregate trivially, like linear regression or logistic regression, but not these more intricate latent variable models, which says then that what you really should do is type equals 2 level, which gives you correct chi-square and standard errors. That's a safe route to take when it comes to factor analysis and structural operation modeling. Here is a special case. IRT stands for item response theory. Item response theory, all that means is that you have a factor analysis model with categorical outcomes. So you have a continuous factor and you have categorical outcomes. I mean, denote those by U here. So these relationships here are these logistic regressions. So you should think here, although it's a straight line, you should think an S-shaped probability curve here. So it's multivariate logistic regressions. So the logistic regression in IRT language is called a 2-parameter logistic. 2-parameter being the intercept and the slope. There are 3-parameter logistics too, where you have a guessing component, a lower asymptote that's greater than 0. And there's a 1-parameter too, which is often called a Roche model. In any case, the within-level model is like this, and you think of it as a random intercept model. So for each of these 4 indicators of the factor on within, you have a filled circle saying that the measurement intercept or threshold, we use those terms interchangeably, are random variables that vary across the between units. So they are continuous latent variables on between. And we explain their covariation, variation and covariation, by a between-level factor FB. FB. And one way of looking at that is you have a continuous latent response variable, U star, which you're familiar with if you've gone to our previous course days. Last time spoken about, I think, in the fall. You can write then the variation in U as a between factor variation and a within factor variation and a within residual here. Two things to be said about this formula. One is we have no between level residual here. We could have one, but very often, typically in these applications, between level residuals are fixed at 0. We're going to come back to that statement several times this afternoon. You don't have to make that restriction in Mplus, but very often between level residuals are so small, residuals on the between level are so small they can be fixed at 0. So you note that there are no residual arrows going into the U's on the between. There are no between level residuals. That's why you don't see an epsilon sub bj here. I'm going to repeat that statement in a more interesting context later on. The other thing you see here is that often in two-level IRT, you say that loading is the same for the two levels. So we have the lambda b equals lambda w case here specified. That may not be realistic, but it's often made, that specification, so that the factor variation is all that's broken up in the between and within part. So two-level IRT is easily done in Mplus, and here's how you set it up. You have categorical variables U1 through U6, a cluster variable, say type equals 2-level, estimation ML, you do integration numerically, and on the within level you have this model. To specify that the loadings are equal across levels, you use the parenthetical expression there for the loadings. FW by, the first loading is fixed at 1, but then the statement continues all the way down to the end of the semicolon. So the FW by U2, and by, for those of you who weren't here yesterday, by means measured by, measured by. So the factor is measured by these 6 indicators. And the loadings number 2 through number 6 are given the labels 1 through 5. And the same labels appear on the between level, saying therefore that lambda b is equal to lambda w. That restriction is imposed here. Again, by deleting these numbers, you don't hold the loadings equal, and it would probably be a better fitting model. We'll get into talking about when and where loadings might be unequal in a second. But this is just quickly introducing you to multi-level factor analysis of the continuous outcome type and the categorical outcome type. If you look at slide 75, model results, on the within level FW by, what are you looking at here? Linda said that the type of model used is a function of what the dependent variable scale is. The dependent variable here is U. It's a categorical dependent variable. So in this statement, F is measured by these variables, says that the U variables are regressed on FW. U is regressed on FW, implying that we are talking about logistic regression coefficients here. Logistic regression coefficients. So a positive significant regression coefficient says that FW has a significant positive influence on the probability of the U's being 1 as opposed to 0. For increasing FW, the positive slope says that the probability of U equals 1 as opposed to 0 increases. You have a within level factor variance, and you have a between level factor variance at the bottom here. And it's the between level factor variance being greater than 0 that causes the interclass correlation, causes the non-independence of observations. On the between level, we have FB by these U's. Maybe we need to have the picture in front of us again. So on the between level, the random intercepts are correctly portrayed as continuous latent variables, and therefore these regressions are linear. Linear regression because the dependent variable is continuous, whereas here the regressions are logistic because the dependent variable is dichotomous. So FB is measured by these variables, which is the Mplus way of saying that each of these variables is regressed on FB, but it's a shorthand form of saying that, and therefore these are linear regression coefficients over here. Standard linear regression coefficients, just like in regular factor analysis. I get it. So I think at that point we are supposed to stop and take a break.
We'll take questions.
Take questions first,
Before
yes.
lunch. Yes.
Can we, after we run logistic regression, can we have the predicted probabilities?
No. You can't save the probabilities, but we do give you the probabilities in latent class analysis if there are no covariates. But for a situation where you have covariates in the model, we would have to give you probabilities for whichever values of the covariates you want, and that would be complicated to do. So in that situation, we don't.
But for simpler cases, that is pretty high on the wish list that we have. The wish list is just very long.
Way back there?
I was wondering, could you go over again how in the between component, how did, like, for instance, high school dropout, how did it become a continuous variable?
And which slide is that on? Do you have that handy?
52.
52?
Uh-huh.
So I couldn't really answer.
So I think you were asking about how this random intercept became a continuous variable.
Right.
Is that what you asked?
Right. Yes.
So remember when I talked about two-level logistic regression, which is this part, I was saying that you had an alpha sub j here, namely an intercept that varied across classrooms. You know, it was an intercept for juvenile delinquency there. So that is an intercept that varies, and an intercept is always a variable that is a quantitative thing that is therefore a continuous variable. It's something that can vary from minus infinity to plus infinity on the real line.
Well, on the scale of high school dropout, yes and no, how does that mean someone would start at a yes or start?
Yeah, so then you have to go back to the, it's good that we penetrate that. So the alpha that we're talking about is this alpha, and that is, although that varies from potentially from minus infinity to plus infinity, it gets to influence the logit, influence the probability. So it's an alpha if you go further back here. It's an alpha that sits here at the intercept over called beta 0. So it will influence the probability by shifting this probability curve sideways. And very high alphas then will shift the curve this way so that the probability gets higher, just like it was for smokers. So although the random intercept is a continuous variable that can be like 50, it will be moderated by this squeezing function, which makes it into probability. And therefore, probability will still be between 0 and 1, as it should be.
Any other questions?
You can.
Yes.
On page, slide 61, 62 for the two-level implementation. Two questions. So, found that the power estimate was about 0.55, but then if you were to increase, for example, the number of clusters, probably that
should increase power.
That would increase power.
Yeah.
You might expect, and that might be one way to see whether or not.
That's right. So we got power 0.55 to detect that the mediation effect, the indirect effect, was significant. That was for 100 clusters of size 10. Probably the most bang for the buck would be obtained by increasing the number of clusters. The sample size on the between level. I agree. But it would be interesting to see. Okay, I increased that to 200. How does that compare to staying at 100 and increasing this to 20? Measuring all the kids in the classroom, for instance. It'd be interesting to see what the pros and cons are there.
And then in terms of the model constraint that you specified to actually estimate the indirect effect.
Right.
Can you explain the new, that might be part of the Monte Carlo, I guess, but I'm not, what is the new line?
What you mean, what is new? The new option? The new option just names names M. It gives, M is not either an observed variable or anything we can label in there. So we have to have a way of giving it a name.
So
new just gives a name that we can then use to define a parameter.
So new, the association you should get is a new parameter that was not mentioned in the model. So it's a parameter that you add to the model. The parameter is the indirect effect, which is a function of three parameters that are part of the model.
Right. So see, we could label MA, MB, and use them down here because we labeled them, but there was nothing here we could label M because it's something new.
It's a function of other parameters.
So we have to give it a name or a label to use it in model constraint.
And by 0.3 then?
Wait, I'm sorry.
0.3 is just the starting value, which happens to be the true population value in this case. And
Which is used for coverage.
You give the true population value as a starting value here. That means that you get the coverage computed in the correct way, the second to the last column.
And so using a model, the typical model indirect statement in Mplus will not give you the correct estimate and standard error of the indirect effect
in a random slope setting. No.
Random slope setting.
So we don't have model indirect for random slopes.
Right, exactly.
We have the type equals 2 level.
Oh, I see. That was your question.
2 level
All right.
random.
Oh, well, we sorted that out. Great. Yeah, not automatically, but you have to do it through modeling indirect.
Right. Yes.
Model constraint.
I'm sorry. For this same model, because there's no comment says N is regressed on X and Y is regressed on X and N. Where are those statements?
I think I don't understand.
Y is regressed on X, Y is regressed on M.
Oh, both. Okay.
Yeah. But you just split it up. You talk about one partial slope here and another partial slope there.
Okay, I ignore it.
Yeah.